In the last few lectures, we were discussing the oscillatory flow in a pipe. When there is an oscillatory pressure gradient that is applied across the ends of a pipe, and this pressure gradient has an oscillatory variation with time. We wanted to know what is the unsteady velocity field. The unsteady but fully developed velocity field, that is, there is a variation in time, but the velocity does not vary in the x direction, the axial direction, and the pressure is a linear function of the axial direction, though it could be a function of time as well. And the pressure gradient in the axial direction is independent of position, it depends only upon time. And the inhomogeneous term that we had used here was of this form. The pressure variation in time, the variation of the pressure gradient in time was considered to be of the form k cos omega t. Okay. And we had solved this problem. Okay. So, first is we had scaled the equations, we had scaled velocity by the viscous velocity scale, okay, the velocity by the viscous velocity scale, the time by the frequency or the inverse of the frequency. Frequency is 2 pi divided by the time period. So, basically we are scaling time by the time period of the pressure perturbations, and we scaled radius by the radius of the pipe. Of course, the distance from the axis was scaled by the radius of the pipe. And from that we got one parameter, which is the Reynolds number, okay, Re omega, based upon the frequency and the radius of the pipe. Now, the conservation equation was of the form given here, okay. Re omega times partial Vx by partial t is equal to minus of cos t plus the derivative with respect to r of the velocity. Okay. So, the term on the right side is the viscous term, the second term on the right. First term is the driving pressure gradient, and the term on the left is the inertial term. And we had substituted, instead of cos t, I had said that you can take the inhomogeneous term as e power I t, because we know that cos of t is equal to the real part of e power I t. Okay. Therefore, if I solve the momentum conservation equation with e power I t as the inhomogeneous term, as the driving force, the solution for the velocity field will also be complex, because the driving force is complex. If you take the real part of the complex solution with the driving force as e power I t, you get the solution with the driving force as cos t. Okay. So, that was the rationale that we had used for replacing the driving force by e power I t. Okay. And this can always be done. Okay. So, if you have a certain driving force which is complex and your actual driving force is the real part of that, the solution for the velocity is the real part of the solution for the complex velocity obtained by solving the conservation equation with a complex driving force. Further, if the driving force is exponential, it has a time period of omega, okay, and the equation is linear, that means that the velocity also has to have that same frequency. Okay. That is easily observed by actually multiplying, expressing the velocity as a spatial function times e power I t, substitute in the equation, and all the time dependence will disappear, okay, because that factor of e power I t cancels out on all terms in the equation, and you get an equation that depends only upon r for this function v tilde of r, okay, which is only a function of r. Recall at the beginning I had told you that in general the conservation equations are partial differential equations. There is no general way to solve partial differential equations, and therefore, we have to use physical understanding to reduce it to an ordinary differential equation. And in this case, the reduction to an ordinary differential equation came from the physical understanding that since it is a linear equation, if the forcing is of a certain frequency, then the response also has to be of the same frequency. Therefore, I can express the velocity as some function of radius times e power I t. Okay. Of course, that function could be complex. Having a complex function of radius will basically result in a phase shift in the solution for those who are familiar with the response to a oscillatory driving force. So, we had got the solution for this V tilde. Okay. It was in the form of a Bessel function. Okay. We had got an explicit solution for V tilde, and this was in the form of a Bessel function. Okay. In Bessel function with a complex argument, okay, a Bessel function with a complex argument. Okay. And then this complex velocity V plus is V tilde of r, okay, times e power I t, okay, is V tilde of r times e power I t. Okay. V tilde of r times e power I t. Okay. So, I have to take multiplied by e power I t, take the real part, and then I will get the real velocity. Okay. And you can solve this numerically. Okay. And I was trying to show you what will be the pressure gradient, okay, the velocity at different points along this pressure pulse. Okay. Note that the pressure pulse was cos omega t, okay, times k. Okay. So, if I take dp by dx, okay, so I should actually take divided by k, okay, or cos of, okay, t star, k versus t star, okay, the scaled, where t star is omega t, and I can plot the velocity at different instants in this sinusoidal variation for different values of the Reynolds number. Okay. So, if I take R e omega is equal to 0.1, for example. Okay. So, basically what I will plot is, okay, from the center, okay, I calculate the radius from the center. Okay. R star is calculated from the center, and as a function of the distance from the center, I am plotting the velocity profile. Okay. So, it has to come, the velocity has to be 0 at the center, and it has to have 0 slope at the axis. Okay. So, this is the axis and this is the wall, and this is the axis. Okay. And at different points in this phase, I am plotting the velocity field. Okay. So, it will look something like this. Okay. So, if I plot R star, okay, this is the center and this is the axis, R star is equal to 1, okay, and on the x axis Vx star, okay, I put the origin here, okay, because velocity is going to be both positive and negative. Okay, the velocity is going to be both positive and negative in this case. Okay. So, at time t is equal to 0 at this location here, okay, at the location at time t is equal to 0, the pressure gradient is positive. Okay, the pressure gradient is positive, right. That means that the pressure increases with downstream distance along the pipe, and therefore, the velocity has to be negative. Okay. The velocity will have a curve that looks like this, it will be a negative value, okay, at that location, when the pressure gradient has a maximum positive value. Okay. At this point where the pressure gradient decreases, the velocity will look something like this. Okay. This is for R e omega is equal to 0.1. Okay. And at this location where the pressure passes through 0, you will have a small, okay, a very small, but a slightly negative value. Okay. Then as it goes on the other side, okay, at this point, right, the pressure gradient has become negative. So, the flow has to be in the positive direction. Okay. So, you will get something that goes like this. Okay. Then when it goes to the other maximum, when the pressure gradient has a minimum, right, that means that the pressure gradient is negative, that means that the pressure decreases downstream, the flow velocity will have the maximum positive value. Okay. And then it will once again decrease in the other side of the cycle. Okay. It will decrease on the other side of the cycle. For example, in this case, it will look something like this. Okay. And then on this, once again when it passes through 0, it will have a small value, and then it goes to the other side. Okay. Then it goes to the other side where it is a yellow. Okay. So, in this case, this yellow will be slightly below, okay, and so on. Okay. So, that is the way that it will change as for different periods. When the pressure is a maximum positive gradient, that means that the pressure increases with downstream distance. Outlet pressure is higher than the right side pressure is higher than the left side pressure, and that means that the flow is in the negative direction, and that is this first red curve here. Okay. So, on the other part of the cycle, I will plot it with dashed lines, okay, so that there is no confusion. Okay. When the pressure gradient is negative, I am plotting the velocity with dashed lines. Okay. And this one will also be a dashed line. Okay. And so will this one. Okay. So, this is the value of the velocity field as a function of time. Okay. In this case, when RE is 0.01, okay. When RE is equal to 0.1, say, okay, you get something that looks very similar. Okay. So, the first is this red point here. Okay. It will be a maximum in the negative direction. Okay. So, it will look something like this. Okay. Then the next curve is when it is slightly below. Okay. You get something that looks like this. Okay. And then at Vx star is equal to at this point, okay, the green point when it passes through 0, okay, when the velocity passes through 0 at this green point here, you get something that is a little more negative. Okay. It is not quite 0. Okay. Okay. And then, so it is not quite that. So, let me just plot it a little bit better. Okay. And then it goes on the other direction. Okay. At this yellow point here, you get something that goes like this. Okay. Then at the maximum red, it goes to the maximum on the other side. Okay. Okay. And then this blue point, okay, it starts coming backwards. Okay. So, it comes something like this, and then at the green point it once again comes like this. Okay. So, the velocity is not quite 0 when the pressure gradient passes through 0 in this case. Okay. The velocity field at the green points, for example, you will see that the green curves are not 0. Okay. So, in the case of RE omega of 0.1 as well, the green curves were not 0, but they were very small. In this case, they turn out to be larger. Okay. And this trend continues, okay, as you increase RE omega. apologies here, this should be R omega is 1, okay. This is when R omega is 1 and this is when R omega is 0.1. Okay. So, I am increasing R omega by a factor of 10 in each case. Okay. In this case, when the pressure is a maximum, the velocity is not actually a maximum. Okay. When the pressure is a maximum, the velocity is not actually a maximum. Okay. The velocity becomes a maximum at this blue point. Okay. At this blue point is when the velocity becomes a maximum. Okay. And then at the green point, it does not quite go through 0. Okay. At the green point, it does not quite go through 0. Okay. It looks something like this. Okay. And then at the yellow point, okay, the velocity is still non-zero. Okay, it looks something like this. Okay. And on the other side of the cycle, you get this is not a maximum. Okay, in the other side, the at the yellow point actually it has a, it looks slightly different. Okay, so. And then this cycle repeats itself. Okay. At the blue point, it is close to its maximum on the other side. Okay. And then it retracts once again. Okay. It comes back at the green point. Okay. And then at the yellow point, it looks something like this. Okay. So, you can see this is clearly complex. Okay. You are getting a phase shift, okay, between the pressure wave and the velocity. Okay, you are getting a phase shift between these two, and that phase shift actually accentuates as the Reynolds number increases. Okay. So, if I plot it for Re omega is equal to 100, okay, R star, this is 1, this is 0, this is 0 velocity. Okay. In this case, the velocity is actually close to a minimum. Okay. At the when the pressure gradient is a maximum. So, if I look at it at this point where the pressure gradient is a maximum, the velocity actually looks something like this. The velocity actually looks something like this. Okay, it is virtually 0 when the pressure gradient is a maximum. Okay. And then at the blue point, it looks something like this. Okay, at this location, okay, when the pressure gradient is decreasing. And at the green, it actually, or the pressure gradient is actually 0, that is when the velocity is actually a maximum. Okay. It looks something like this. Okay. And then when it retracts to the yellow point, okay, when it goes negative, okay, the velocity actually looks it looks something like that. Okay. And you see that cycle repeating over on the other side. Okay. So, at this blue point, it looks something like this. Then the next one will go to its maximum, okay, at the green, and then at the yellow it will look something like this. Okay. So, you can see that there is a clear variation in the nature of the velocity profile as you go from low to high Reynolds number in this case. At low Reynolds number, the velocity is a maximum when the pressure gradient is a maximum. when the pressure gradient is a positive extremum, the velocity is a negative extremum, okay, it is in the opposite direction. Similarly, when the pressure gradient is negative, the velocity is positive. In contrast, at high Reynolds number, the velocity is 0 when the pressure gradient is at an extremum, okay, or nearly 0 when the pressure gradient is at an extremum, and it goes to a maximum value as the pressure gradient goes through 0. So, these are two very different characteristics. Okay. The other important difference is that the velocity profile looks parabolic when the Reynolds number is small. Okay. The velocity profile looks parabolic when the Reynolds number is small. On the other hand, when the Reynolds number is large, okay, the velocity variations are actually restricted to a thin region close to the wall, greater than about 0.6 or so, okay, for Reynolds number of 100. Okay. Below that, okay, within for R star less than about 0.6, the velocity is virtually a constant. Okay. It is virtually like a plug flow for R star less than about 0.6, and the variation is only in the region close to the wall. So, these are the two salient features of the velocity profiles in this case. So, to recall, we actually managed to get a solution for the velocity profile, okay, but it was the real part of some complex function which is a product of functions of time and position. Okay. And if we solve it numerically, we get these kinds of results. So, the question is how can we understand this? Okay. How can we understand this? Can we use some physical reasoning in order to determine the nature of the velocity profile in the limit of low and high Reynolds number? Okay. So, first things first, the Reynolds number is equal to rho omega square omega r square by mu is equal to omega r square by mu. Okay. If I write this in terms of the time period of oscillations, okay, omega is 2 pi by the time period of oscillations, okay, into r square by nu, okay, okay, which is equal to 2 pi by the time period of oscillations into r square by nu is the viscous diffusion time, okay, the viscous diffusion time over a distance r. Okay. So, the Reynolds number is the ratio of the viscous diffusion time over the distance r divided by the time period of oscillation. If the viscous diffusion time is much smaller than the time period of oscillation, right, then momentum diffuses rapidly across the entire cross section of the pipe within the time it takes for the pressure gradient to change. Okay. When the viscous diffusion time is much smaller than the time of oscillation, the momentum diffuses instantaneously, rapidly across the entire cross section within the time it takes for the pressure to change, okay, due to the pressure oscillations. So, in that case, you would expect the solution to be the same as what you get if you had a steady, okay, you would expect the solution to be the same as the steady solution obtained for that particular instantaneous value of the pressure gradient. So, whatever the instantaneous value of the pressure gradient, momentum diffusion is fast compared to the time for the pressure gradient to change. Therefore, if we assume the pressure gradient is a constant and calculate the steady solution, that should be the solution in the limit r e omega small compared to 1. Okay. The velocity profile will be the steady profile for the instantaneous. Of the pressure gradient. So, recall that we had calculated the velocity profile. Okay, we got that V x, right, is equal to minus 1 by 4 mu dP by dx into r square minus r square. Okay. Or alternatively, in scaled variable I can write this as minus r square by 4 mu dP by dx into 1 minus r star square. Okay. This is for a steady flow. Okay. This is for a steady flow. Okay. If for this particular pressure gradient here, okay, I substitute the instantaneous value. Okay. If for this I substitute the instantaneous value of the pressure gradient for an oscillatory pressure function, okay, then my solution for Vx will be equal to minus r square by 4 mu k cos of t, okay, into 1 minus r star square. Okay. Okay. And you recall that in this problem we have defined the scaled velocity Vx star is equal to Vx by mu by r square k. Okay. So, this just becomes equal to minus cos of t star into 1 minus r star square. Okay. This is minus 1/4. So, this is the velocity profile, the parabolic profile in the limit of low Reynolds number, where the velocity field is responding rapidly or almost instantaneously to the instantaneous value of that pressure gradient at that instant of time. Okay. You get back the parabolic velocity profile, and those parabolic velocity profiles are what you saw over here. Okay. At r is equal to 0.1, the velocity profile is close to a parabolic velocity profile, with amplitude corresponding to that particular instantaneous value of the pressure gradient. Okay. And this happens when the time period of the pressure variation is much longer than the diffusion time, so that the momentum diffuses instantaneously across the entire pipe within the time it takes for the pressure to change. Okay. So, that is in the limit of low Reynolds number. And as you can see, the behavior in the limit of for high Reynolds number is very different. Okay. So, how can you explain the variations in the limit of high Reynolds number? I will continue this in the next lecture. We will look at how we can improve the approximation for low Reynolds number, as well as how we can get an approximation for high Reynolds number. I will continue this in the next lecture. I will see you then.